none of that turns the clock as a whole, only the external torque I apply changes the angular momentum of the system. So if we looked inside here, right, we could see if these gears are turning like this, right, this one has spin into the page, this one has spin out of the page, they're going to cancel out. So if I draw a box around the thing I call the system, right, that system as a whole, its angular momentum only changes if there's some external torque. So the torque that these gears are exerting on each other, because that's not something coming into the system or going out of the system, they don't affect the total angular momentum of the system. So this is pretty similar to what we were talking about when we talked about linear momentum and energy. As long as there's no forces going in or out of the system, I have conservation of linear momentum, I have conservation of energy. Here it's the same thing. As long as there's no torques going in and out of the system, which is really just forces, as long as there's no torques going in and out of the system, the angular momentum of the system doesn't change. In other words, torque, so if torque net external equals 0, then L system equals some constant. It's a very simple statement, but it's extremely powerful because this is the law of conservation of angular momentum. Right? Us scientists, only when we're extremely confident about something do we call it a law. Right? So this is something that we're extremely confident about. That angular momentum is conserved in the same way that linear momentum is conserved, in the same way that energy is conserved. Right? And it's important to point out that they're all conserved separately. We could see systems where the energy is not conserved and the angular momentum is. Right? In the same way that we had systems, aka inelastic collisions, where we had conservation of momentum, we did not have conservation of energy, right? So conservation of angular momentum, conservation of linear momentum, and conservation of energy are the three fundamental conservation laws for mechanics, right? There are a couple other conservation laws out in nature which don't really concern us during this class. For example, conservation of charge. Okay, so this is a fundamental conservation law for the universe. So the universe as a whole, unless there's something outside of it doing stuff to it, should have net zero angular momentum. Okay, I'm going to do an example, but before that I just want to quickly derive a useful equation, which is we have relationships between torques and angular momentums, and between kinetic energies or rotational kinetic energies and angular velocities. So it might be useful to have a definition, or rather a relationship between rotational kinetic energy and angular momentum, and it's oftentimes useful to write down this equation. So kinetic energy of rotations, as we learned on our first class about rotations, is equal to 1/2 I omega squared. And then our angular momentum for a symmetric system is I omega. So I just gotta move this I over here and then plug in that omega there. So isolate this omega and plug it in there. And I get the kinetic energy of rotations equal to L squared over 2I. Okay. So if I have a simple symmetric system rotating, I want to find the kinetic energy. I can get at that just by squaring the angular momentum and dividing by 2 times the moment of inertia. All right, which again is similar to our kinetic energy for linear systems, where we had p squared over 2m. Okay, so let's do an example. So we're going to do an example of a ballistic pendulum. So what is a ballistic pendulum? So here I have some thin rod that's on a pivot, and I'm going to fire some object at it. So we're going to say that this object in this example is a piece of clay. Okay. But it could be anything, right? If one way to this is why it's called the ballistic pendulum, one way to measure the kinetic energy or velocity of an object that's fired really quickly, like a bullet or something like that, is to fire it at a block that's sitting on a pendulum, and then if the moment of inertia and mass of the ballistic pendulum are known, we can tell how much energy and therefore how much velocity was in the object by how far back this thing swings after it's been hit, right? So we're going to do an example of a ballistic pendulum, but now for a system where we can't use energy because this is going to be a lump of clay that's going to get smooshed as it hits this thin rod, and therefore is going to be losing some energy. So we're going to have to use concepts of momentum, and specifically, of course, concept of angular momentum. So let's label all this stuff in here. So this lump of clay, however you fire a lump of clay, maybe like a potato gun filled with clay, I don't know, and it has some mass. The ballistic pendulum, of course, has some mass, which we're going to call capital M. Right? And in case this isn't clear, this is a pivot here, so this thing can swing back and forth like that. This lump of clay is going to hit some distance x down. Well, this should be drawn from the pivot. Down from the pivot. And the total length is going to be d. Right, so a bit longer than the place where the clay impacts the ballistic pendulum. So this is a question from, I think, the old book. So I'm just going to read it now that I've explained the geometry. A thin rod of mass m and length d hangs from a pivot attached to one end. A piece of clay mass lowercase m and moving horizontally at speed v hits the rod at distance x from the pivot and sticks to it. Find the ratio of the clay rod system's energy just after the collision to its kinetic energy just after the collision. So what we're looking for is how much kinetic energy has been lost. Right, again, the energy goes into smooshing the clay and heating it and making the little sound it makes when it hits the, I don't know if that's what clay sounds like, when it hits the rod. So the first thing we want to do is find the kinetic energy initial, which is going to be 1/2 mv squared. Before the collision between the clay and the rod, it's just the motion of the clay. The rod is still. So it's just 1/2 mass of the clay times the velocity of the clay. So, but after the collision, we have the whole clay rod object, because remember the clay has stuck to the rod. You have the whole clay rod object is going to be in motion. So I know that my kinetic energy final is going to be L of the system squared divided by 2 moment of inertia final. Okay. So during the collision, the angular momentum is conserved. We do not have conservation of energy, but we have conservation of angular momentum. So we need 2 things now. We need this angular momentum and we need the final moment of inertia. So the angular momentum of the system, right? We're just going to be concerned with magnitudes. So R cross MV, right? Our R cross P going to be MVX, just the moments before this clay hits the rod. So just that little instant before the clay hits the rod when it's just barely touching it but hasn't imparted any of its momentum yet, I'm going to have mvx. Okay? The v is going totally in this direction. The r is totally this direction, so they're perpendicular. So that sine of 90 degrees is 1, so I just have mass times velocity times the distance down from the pivot to where it impacts. And since angular momentum is conserved, this is going to remain the angular momentum of the system after the impact, right? Because if we draw a box around this object, well, there's no forces or torques going into the system. We're losing energy, of course, because we're losing energy to internal degrees of freedom when that clay hits the rod. Now we need to know the moment of inertia, IF. Well, we're going to add up the moments of inertia of the various components of the system, which are two components. So the first is going to be, you imagine this thing is swinging. We're going to have a moment of inertia contribution from this ball of clay, which is going to be smushed up against the rod. So let's assume that in this perfectly inelastic collision, this clay is just stuck there and no bits of it have fallen off or anything like that. So it's all still stuck on there. And then our moment of inertia is just going to be mx squared, the mass of the clay, times the distance, right, the radial distance, which is just this x. And then I look up the moment of inertia for a thin rod rotating about its endpoint, and that's 1/3 md squared. Right? The mass of the rod and the distance, or rather the length of the whole rod. So now I can calculate my kinetic energy final by just plugging in a bunch of stuff. So I'll skip over that algebra, but if you want to go through that, you can just pause the video and go through it and see if you get the same thing that I get, which is maybe a good exercise. Oh, whoops, I wrote it wrong. I was looking at two different lines in my notes that had different things on them. And then my kinetic energy initial is just this guy here. So how much kinetic energy is lost? We're going to set that up as a ratio, kinetic energy final over kinetic energy initial. Again, I'm going to skip over the algebra, but you can do that yourself if you want to practice, which I recommend. Even though we're having this weird classroom right now, there will still be tests. Not quite sure what form they will take, but I'll figure that out eventually. Okay. So the amount of kinetic energy that's lost depends upon this ratio here. So if this thing was 0, right, this little subfraction here were 0, we would have total conservation of energy. But we only get that if that mass of the rod or d of the rod goes to 0. So, that ain't going to happen. So the point is that for this ballistic pendulum, now that we know all the geometry of it, right, we could figure out something about the system if we didn't know. If we knew the d squared and the k squared, and we also know the m, or both m's, then we could figure out, well, what's the final kinetic energy, or what was the initial kinetic energy? Okay? So if you wanted to find out something about this flying lump of clay, like your friend's throwing lumps of clay and you want to find out how good your friend is at throwing lumps of clay, you would use this equation. Okay? In case you want to know that. Okay, so that's all I wanted to get through today. Next class, we will continue talking about torque, but we're going to pivot a little bit. Oh, I didn't realize that's kind of a joke. You should laugh now. Laugh at my pivot joke. I'm gonna just imagine you're laughing at all my terrible jokes, which is maybe better than class, where I can see that you're not laughing. Yeah, this is maybe better for my self-esteem. Yeah, so next class we're gonna talk about torque as it applies to statics, right? So those of you who are taking, I guess, mechanical or civil engineering, you'll have a whole class about statics. So this will be a little intro to that, right? We'll just do some simple systems. And of course, the key thing that's going to be of interest will be torque. Okay, so again, all of you should go and sign up for the Reddit account for the forum if you haven't done so already. About half of you have done that, I think, but as of when I'm recording this, there aren't any questions on there yet. So please go on there, please ask some questions, please help me kill a bit of time while I'm trapped here in my apartment by answering interesting physics questions. Hope everyone is doing very well, and have a nice weekend.